I want to start with the premise of my research and in a very soft way. And by the way, I didn't frame the talk in a very technical, heavy fashion. But if you want to have details about models, details of formulas and so on, just feel free to ask. I thought I didn't want to give a sleepy presentation full of technical details. And yes, and I want to start with the premise of my research, sorry, the concept we build everything on. And yeah, and since we are going to have the Olympics, postponed Olympics during the summer, I thought it's a good way to remember some of the characters that of the last Olympics in Brazil. And I hope that among some of you there are fans of sports, and I address those especially. And I want to ask you if you remember who won the 100 meters sprint in the male category at Rio in 2016. Feel free to shout it, unmuting yourself, or to type it in the chat. Usain Bolt? Yes. So this was the fastest answer. I'm sure that there were other people thinking about this. So Usain Bolt won the 100-meter sprint with this timing. But now I have the question about who won the second, the silver medal, the second place. And please don't cheat and type, right? Any guess? Gatling? Okay, Niels is probably a fan.
Yeah, I
Actually,
am.
yeah, okay. So it's Justin Gatling. Usually, most of the people don't know the second one. So, or everybody knows Usain Bolt, and very few know that Justin Gatling was the second one. Notice that it was just very few milliseconds slower than Usain Bolt. Look at the numbers. And what about the bronze medal? Any guess? This is the hard one. Everybody tells me it's really the hard one, even those that are fanatics about this. So Andrea de Grasse is the third one, the one that won the bronze medal. Again, with a time that was very close to the one of Usain Bolt and Justin Gatlin. So this is times reflect the performance of these three athletes. What we can do is also looking at the popularity of these three athletes, for example, on Google searches. This data come from August 2016. What I did is just typing their names and seeing the search results. You can do similar things by looking at number of views in Wikipedia or using social media. What you can see if we type the names of these three athletes is that Usain Bolt has the highest number of searches, Justin Gatlin is the second, and Degas the third. But the differences between these numbers are huge, are not just a fraction of. So the differences are covered different orders of magnitude, while their performance differences are just a fraction of a second. So if you want to visualize this, if we rescale the font size of the numbers proportionally to the value, we would see that there is basically no detectable difference in the timings, while we see huge differences in the popularity in the searches on Google. And the number of Andrea de Grasse is actually there, it's just very tiny. So this example shows the difference between what I call performance and what I call success, which is the premise of my line of research. So performance is, in this case, would be the speed of the three athletes, while success is captured by the popularity, so by, for example, Google searches, Wikipedia views, or presence or popularity on social media. And so why am I highlighting the difference between performance and success? So performance is about you. It's an individual attribute. Is the speed of an athlete, is the work, the painting of an artist, or the paper of a scientist. Instead, success is about us, is how reflects how society perceives the performance of an individual. So it's a social phenomenon. And why is this important? Well, it's important because we often work under the assumption that if you do something good, automatically you're going to be successful. So that performance and success are linked. And even without realizing it, even without thinking twice about it, we often use success, or call it popularity, visibility, to gauge as a proxy of performance. However, there are many works that show that the connection between performance and success is not trivial, and it's also it's not well understood. So one of the works that I love, that I'm a fan about, is the paper by Salganik, Dodds and Watts in Science in 2006, the Music Lab experiment, that shows with a controlled randomized experiment that in the context of music, that there is a very poor correlation between quality of music and their success. So they showed with parallel randomized experiments that the same song in one experiment could become the best one, the most downloaded one, while in another experiment it could be actually the one performing the worst. And this happened because of the presence of social influence. So back in 2013, I was reflecting about the connection between performance and success, and especially I was focusing of their relation in science. So how do we think about performance or quality and success or impact in when we look at science and scientists? And so I'm going to take a bit of a historical tour of how I was thinking about success and performance in science. So we'll touch briefly on the first work that I did, and then mention more of the recent stuff that built on that work. And the first question that I had, back in 2013, 2014, and that I developed over 2-3 years was, how does success in scientific careers evolve? So I was focusing on success only. And later I started thinking about the relation between performance and success in science. In particular, I had these two questions. Who is going to have an outstanding achievement? So which scientist, and when in a career? And to do this, we wanted to create models and validate models of how success evolves in a career. And we had a strongly data-driven approach. So we were working with publication data sets, publication and citation data sets. And what I show you was built on 2 different data sets with different strengths and weaknesses. So one is a data set of about physicists. It's just about one discipline, but spans over 110 years. So it's highly longitudinal. The other data set is more recent, so it's focused on the last 30 years, spans over 6 fields. And doesn't matter which data set you use, the results are similar, which is nice. So we are not picking a characteristic of a specific data set. And when I talk about careers, so we were studying scientific careers here, I have in mind something like this, like the one that you see on screen. So this is the career of Richard Feynman. And on the x-axis, you find the time of the career. So, and each red dot in the plot represents one of the publications of Richard Feynman. The x coordinate of the red dot is the publication date of that paper, and the height of the dot is a proxy of the impact of that paper. So it's a measure of success. And we were interested to understand when Feynman, when scientists publish their highest impact paper during a career. So when, so this time is called the T-star, and how high they score with their highest impact paper. This is just a different way of visualizing career of Feynman. Just smooth it, and it will be clear in a second why I show you also this visualization. Just notice that we are interested in the highest impact paper also here. So this is the highest impact paper is denoted with a star. We can identify the highest impact paper for Richard Feynman or for all the other scientists in the data sets. And we started looking at the properties of these highest impact papers. And when we did this, something interesting happened.
All these careers look different, with valleys and peaks of impact. To identify outstanding discoveries, the team focused on the highest impact publication by each scientist, shown here by the red dots. The data showed that scientists tend to make major discoveries when they are young. This finding matches previous research on creativity. For example, the first line here represents a career of 23 years. This scientist published his breakout paper in year 5. The second line represents a 14-year career, with the highest impact work published in the first year. But when the team examined the reason behind early creative success, they stumbled across something that surprised them. Scientists are simply more productive when they are young, giving them a higher chance of producing that big hit in their early years. If we ignore the timing and only look at the position of the highest impact paper in the sequence of a scientist's publications, we see that the highest impact paper can be, with the same probability, anywhere in the sequence of papers published. It could be the first publication, it could appear mid-career, or it could be a scientist's last work. In other words, impact is randomly distributed within a scientist's body of work, regardless of discipline, a result the team named the random impact rule.
So basically, the very first thing that we did was to look at when scientists did their best work. So this could be at year 1, at year 2, at year 3 in their career. And this was really one of the first plots that we did. So we plotted this frequency, and we saw that scientists are more likely to do their highest impact work in the first 20 years of their career, and then there is a sharp decline. But the question is, what is the expectation for this kind of plot, given that people have different productivities throughout their lives, throughout their career? This is a result that social psychologists know very well, so that productivity can be very heterogeneous. So we created a null model of careers where we basically destroyed the correlations between time and impact. As a matter of fact, what we did was to keep the publications, the red dots in the previous plot where they were, and just reshuffle the impact, so the y coordinates. And then we did the same, sorry, okay, so here we reshuffled the impact, the y values among these red dots, and we did it many times for all the careers. And then we repeated the exact same measurement for these randomized careers. And the surprise was that basically we found the same profile. So there is no difference between data and these randomized careers, meaning that the highest impact paper could be the first paper, could be the second paper, or the last paper with the same probability. And this shape is just due to the fact that scientists have more papers in the first 20 years of their career and less paper later. So if I have to pick randomly a paper, this is more likely to be picked in the first 20 years of their career. I don't take this shape, this 20 years, as a magic number, as a magic shape. If you change the data set or if you segment the population different ways, you get different shapes. But you can see that there is always no difference between data and randomized careers, meaning that the productivity can change, but impact is always random within a career. So the highest impact paper could be first one, the second one, or the last one with the same probability. I just want to give you some anecdotal evidence that this is true. So this is on top, you see the career of Frank Wilczek, who won the Nobel Prize in Physics, and he won it for the very first paper that he published. He was still a PhD student. On the bottom, you see the career of John Fenn, won the Nobel laureate in chemistry after he retired. So for work that he did after he retired and after his lab was shut down at Yale and he moved at Virginia Tech. So basically, there is always hope to have your highest impact work if one sustains productivity, if one doesn't give up. So, but the important result here is that the impact is random within a career. And this result was really eye-opening, because I started realizing how much luck can be involved in success. So remember that here we are quantifying the highest impact paper with measures, citations-based measures, which are social measures. So our citations are provided by the scientific community. So they are not a measure of the intrinsic quality of some work. Although impact is random within a career, there are systematic differences in impact between careers. So the blue career on the left here has systematically lower impact than the orange career on the right. So what we did was creating a model that would reconcile the random impact rule and these differences between careers. And what we did was a model that would assign a parameter Q here to different individuals, and Q could be high or low, and the impact of a paper would be the product of this parameter Q, individual parameter, and a totally random variable, which we interpreted as luck for different reasons. That is the same for all the scientists. So basically, a high impact paper, a very high impact paper, is the result of having a lucky draw, a high P just by chance, and a high Q, so a high individual parameter. And this model provides all sorts of testable predictions, can be validated, can be used to rescale distributions, individual distributions, so using something close to renormalization theory for the physicists among you. So it's we have reasons to believe that it's a good model to reproduce the success, the evolution of success in individual careers. So if I go to my original two questions, who is going to have an outstanding achievement? These are lucky scientists with a high Q. So luck and Q are both convoluted together and produce high impact, and when this is totally random within a career. Later, we worked on extending this framework to other fields, not just science, but all domains, well, many domains of creativity, like music, movies, books, so literature writing. And the idea was to understand what is the interplay between this Q, this individual parameter, and luck. And you can imagine this as being a spectrum, a spectrum where you have low luck on one extreme. This is the case of chess, for example, where everything is deterministic and there is low luck involved. And on the other end of the spectrum, there is gambling, which is just pure luck, no ability, no skills. And surprisingly, music, movies, books are more or less in the middle. So luck account for about 50% of the fluctuations and in success, and there are no major difference between these domains of activity, so between music, movies, and books. We thought that it could be at the very different extremes of the spectrums, but they are very similar to each other. So I went very fast, or faster than I usually do through this paper, but if you're interested, it's published, and also there is a whole video from which you saw some extracts, and it's on YouTube, so you can find it with it says Scientific Career Predictable. But this was a bit the turning point. Then, after publishing this paper, I had a turning point in my career, and there is also a turning point in this presentation. So, after publishing this work, this individual parameter called Q started receiving a lot of attention. So media, journals started saying, oh, we have a new parameter, a new way of finding Nobel laureates, or funding agencies were contacting us asking for the queue of different scientists to find their next researcher deserving a big grant. So this is where the moment where I said, oh my God, what have I done? Because let's remember that here we have a model of evolution of success, but we have no idea whatsoever what is the relation between success and performance. So the question was, is Q really capturing something closer to performance or not? Or the more general question was, do performance and success in science differ? And this has become really my obsession in the last few years, because we see a lot of work going in the direction of measuring success, measuring it in a very sophisticated way, by using it without having a clear understanding of the relation with performance and the presence of potential biases in it. So the first thing that I did in this direction was trying to understand whether Q is really a good measure of performance. So we removed luck from success and find this Q, but is Q still closer to success or closer to the intrinsic quality of a scientist? And one thing that we did was measuring the Q, the average Q for female scientists and male scientists, and found that male scientists on average have a Q, so this individual parameter, which is 50% higher than the one of female scientists. And here there is the usual chicken and egg problem. Some people will say, well, this might be because males produce better science, which is possible. Other people will say, no, this has nothing to do with quality. This is due to the fact that you are using a measure that is a social measure and is imbued with biases, including the gender bias. The only way to solve this problem is usually with controlled, randomized controlled experiments. And there is one experiment that I really love on this realm, on basically understanding performance and success in science. It's an experiment done about 10 years ago where hiring committees, scientific hiring committees, were presented with CVs, and they had to evaluate. So different committees had to evaluate the same sets of CVs. The only tiny change between the different committees is that some CVs were reporting the female name, and other CVs were reporting a male name, but the CV was then exactly the same. And the result of the experiment was that scientific committees were evaluating basically the same people, just in one case they believed it was a male, and in another case they believed it was a female. And male applicants were considered more competent. They were more likely to be hired, and they would be offered also more mentoring opportunities and higher salaries. So there is a reason to believe, and there is also a bigger body of literature that shows that the perception of performance in science is affected by gender. So we asked, what is the role of gender then in career differences? And when you work with publication and citation data, we cannot do controlled experiments, but sorry, I will skip this. But what we can do is to have something which is very close to the setting of a controlled experiment by using matched sample. So what did we do? We took the careers that I showed before, the same careers, and we labeled the gender using the first name of the authors. So we were having two sets of scientists, females and males. And when you analyze careers straight like this, just taking females and males, you will find a lot of differences. For example, in representation of female scientists, so there is an underrepresentation, basically almost all countries, all points in times, and all disciplines. And you will find also differences for basically any measure that you do, differences in productivity, differences in career length, differences in impact. So it's very hard. So we measured basically almost everything that you can imagine. The thing, the most important differences that are we found relevant to get some conclusions were the following: that males represent about 70% of the scientific workforce. They have 30% more citations than females. They are more productive, and the higher career productivity was 10% in the 50s and 35% in 2000. So the productivity gap is increasing actually over time. However, females and males have the exact same annual productivity. So how many papers on average are published every year during the career of a woman, during the career of a man. And for this reason, females have shorter career lengths. So the only way to explain the fact that males have more career productivity, but females and males have the same annual productivity is that females have shorter career length. And the reason is that women tend to drop out from academia at a faster rate than males. And this is something not surprising per se, we knew that, but what is surprising once we look at careers that span over 40 years and different disciplines is when this happens during a lifetime. It turns out that women tend to drop out from academia at the highest rate 7 years after they started their career. So this is more or less during the first or the second postdoc, or just at an early tenure track. And this dropout rate stays higher for women and men, even 20, 25 years, 30 years after career start. So all these pieces together show that there are a lot of confounding factors. There are a lot of differences in careers. So it's very hard to come up with a conclusion like an average Q of 10 is better than average Q of 7, because there can be many variables that many confounding factors that do not allow us to make a solid statement about the quality of work of a scientist. As I said, there are ways to go around this problem, and here what we did was using huge data sets, much bigger than the ones that I mentioned earlier, to do something which is as close as possible to a controlled experiment. So what we did, thanks to these very huge data sets, is trying to match all the variables that are present in careers of females and males. So, for example, for each female author in a data set that is an American physicist with a career of 10 years, mostly working at an institute or a given ranking, we found an equivalent American physicist with the same career length and so on, working at an institution of similar ranking. So we would find a match for each scientist in a data set. We did this to create the equivalent of a controlled experiment. The only thing that we wouldn't change would be the productivity in one data set and the impact. And here the results again were surprising. So when we look at the total productivity straight in the population, so without doing any matching, we would find a difference in productivity of 27%. However, if we do a matching based on control, discipline, career length, we would see that the total productivity gap becomes only 8%. So when we manage to do a comparison, which is not apples to oranges, but apples to closer apples, we see that there are the differences between men and women shrink. These differences become basically non-existing when, so the difference is only 0.8%, become non-existing when we look at citations and we compare, we match on all the other variables, including numbers of papers published. So if we want to answer these two questions, how does productivity differ between female and male scientists? This is only just by 8% if we take into account discipline and dropout rate. And there is basically almost no difference if we take into account all confounding factors when we look at impact. So there is a big take-home message here that looking at measurements that are based on citations, even if we remove luck or if we remove all the, if you want, the serendipity in a career trajectory, those measurements are not good proxies of the quality of a scientist. So we should make sure that we match also on all the other variables that are can be closely correlated to the evolution of success, so to the evolution of citations. And here I focused on the on gender bias, or how we think about gender bias in science, because it's the easiest bias to tackle. So we have a gender variable, which is in this case, in this setting, it's just a binary variable. There are actually many more biases. Some of those that we studied is like the reputation bias, the interdisciplinary bias. There are subtle, more subtle biases to uncover and to study, but they're present, and they also affect the way, should affect the way we think about success and how we use it as a proxy of performance. So in short, do performance and success in science differ? They do. And questions that I'm addressing now in my current research are related to why do performance and success in science differ, and how this difference affects our lives. In particular, right now, I'm focusing on how these differences between performance and success affects bias the algorithms that we use daily in our school, in our life as scholars. And this is ongoing research that is funded by two foundations here in Denmark. I'm not gonna say much, so I just want to tell you the idea behind it and where this research is going. I would love to hear more about your thoughts on this. So we probably all of you have know the Matthew effect, the rich get richer effect. It has different names in different disciplines. In natural science, it's called preferential attachment. In mathematician talks about Poya-Earn model. It basically says, in the case, for example, of citations, it says that the probability that the scientist gets cited is proportional to the number of citations that that scientist already has. And we can formalize it with this formula. So where pi I is the probability of a scientist to get a citation. Has been documented in many other many other contexts. Also, the retweeting probability depends on the number of retweets, or the number of views of a movie depends on. So the probability that a movie is watched depends on the number of views that it already has. This effect, the Matthew effect, has been studied a lot in many ways. It's been documented, and we know a lot about it. There is another effect, which is also well documented, but much understudied, which is called the Matilda effect. And the Matilda effect says that there is a bias against acknowledging the performance of women. And it has no mathematical formulation. You don't find usually a dynamical model that captures a term, that has a term that captures the Matilda effect. And again, here the Matilda effect focuses on gender. There is an X effect, we could call it X effect, which is a bias against acknowledging the performance of X, where X could be ethnicity, it could be related to other demographics. But like the Matilda effect, we have no mathematical terms to, or no models that include this effect that have mathematical terms that include these effects. And why is this important? Well, it's important because we use social metrics, and social metrics evolve in a biased and unequal way, exactly because of the Matthew effect, the Matilda effect, the X effect. And algorithms, all the algorithms that we use are based on social metrics. So automatically we have algorithms that can be strongly unequal and strongly biased. So an example, for example, is given by engines like Google Scholar that rank papers based on citations. So a paper with 100 citations, a paper with 150 citations are usually, so the number of citations is part of the algorithms at the core of these engines. And for us, it's probably understandable that a paper with more citations is ranked higher than a paper with less citations. However, these algorithms might be discriminating, because there is a lot of research that shows that works from women are less cited than works from men, for reasons that have nothing to do with the quality of those papers. And this can provide some segments of the population with more visibility and with more recognition. So an important thing that we are doing is understanding how citations evolve in a biased way and how this bias is included in algorithms. And we're doing this by understanding the bias mechanisms that drive the different citation trajectories of papers. And the idea is to use this understanding of the mechanism to create unbiased ranking and provide, therefore, same visibility and same recognition. And here again, I focused on the gender variable, but this can be done with many populations, with many demographics variables. So how do we think in practice about this? And this is, so there was a warning symbol because it's ongoing work. So we just want to pitch it and then conclude on this. So what we're doing is taking data about citations again and construct, for example, a citation network between among people, among scientists. And we can take very simple algorithms like those based on PageRank that take the citation network between people and convert it in with some assumptions into a ranking. So if we have females and males in the citation network, we can ask whether an algorithm is fair, is ranking people in a fair way, in respect to their gender. So on the right here, you see a ranking, and there is a whole body of literature that tackles the problem of fairness. So how do we think of fairness in data, and for example, whether this ranking is fair? So I will not go into that, but one simple concept to understand that captures fairness is called statistical parity, that tries to see whether in a ranking, in the top positions in a ranking, we see the same representation for the different demographics. So for example, we look at the first, say 1% of the ranking, and we look whether we see whether we find women and men in equal representation or in representation proportional to their presence in the data set. So this ranking on the left, if we look at the first 3 positions, is not fair, because we see 2 men represented and 1 woman, while the whole ranking, there is 50% of women and 50% of men. To have fairness, we have to look at the whole ranking, so the N position, where we will find 50% of the men and 50% of the women. So we have statistics, the so-called statistical parity. So we are doing work on this with 2 super talented students here at ITU, and we are quantifying the fairness in different disciplines. For example, by using PageRank on the citation network. And here the results are, I would say, really shocking and discouraging in a way. So if you look at the whole population and you look at the beginning, the top part of the ranking, you'll see that there is an overrepresentation of men and an underrepresentation of women. And we move towards, if we move towards the right, we see that the representation becomes more and more balanced, and we reach statistical parity only if we look at 63% of the people ranked. So only by looking at 63% of the population, we will find the same number of women and men. This is done in the population raw data straight. If you do a matching, like the one that we did before, where we compare apples to apples, the result is more reassuring, meaning that the parity is reached earlier, but we still see an overrepresentation of men and underrepresentation of women in the first 10% of the ranking. This is in psychology, where we have actually the most promising and encouraging results. If we look at economics, we have much higher imbalance. So statistical parity in the true population is reached only at 81%. And if we do the affiliation matching, only at 30%. So this means that if I have my engine that uses PageRank in economics or psychology to rank papers, we will find more papers by men, more papers than women, without a clear understanding whether those papers are really papers that are more worthy to read or not. So here we are still trying to understand how, for example, citation cultures could affect the result that we see. Okay, I'm done here. I talked about many things. I provided many results from different papers, but there is one thing that I would like you to take home, to remember from this presentation, and it's really this difference between performance and success. And what we are doing lately is measuring success in different ways and different forms, and for a reason, because it's easier to quantify success than quantifying performance. So it's easier to count the number of citations of a paper, the number of views of a video, because we have no objective way to measure the quality of a paper or the quality of a video. But there is a problem that these measures are social measures, and we still have a poor understanding of many social phenomena that drive success. And I think as scientists in computational social science, we have really the responsibility, the moral problem of understanding better these measures and algorithms before they are used for taking decisions, before they are deployed widely in society. So I thank you. And it takes a village to do work. So I had many collaborators working on science of science themes, on different projects.